Log on, tune in, find out. Another good idea from Cambridge.
Welcome Richard Booth from Schlumberger, and he's going to talk about inversion of pressure transient testing data. Thank you.
So I'm going to talk about inversion of pressure transient testing data, explain what a pressure transient test is. The people who've been working on this, myself and Kirsty Morton in the new Schlumberger Research Centre in Brazil. And also we've had collaboration from Mustafa Öner from Istanbul Technical University. And this whole kind of looking at this project was set up by Fikri Kutluk, who's one of Schlumberger's research fellows based in Clamart in France. So first of all, quick outline of the talk. So I'm going to explain what a pressure transient test is and what kind of information we expect to get from a pressure transient test as opposed to other kinds of data that you might get in kind of when you're trying to measure geological properties. And then talk about how we're going to approach using the data to infer information about the oil field. Explain the different methods, and key thing here is explaining about how you can actually sample the reservoir the parameters of the oil field, not just produce a most likely image. So pressure transient testing is when you're looking at a well and you start producing from the well. In the very initial stages, you get before you're actually really into the proper production phase, you get a pressure wave response, and it's kind of a diffusive pressure wave that goes through the reservoir, and you can, by accurately measuring the pressure response inside your wells, you can find information about the reservoir parameters from this very early time data. So the time scale for this problem is on the order of weeks to months, as opposed to the real production time scale, which is on the order of years. One of the big differences. So usually there's a kind of period where you start producing from a well and then you shut it in and you measure the pressure response both during when you start producing and when you shut it in, because you get a second pressure response from those. And typically in the past this has always just been matched to simple analytical models, so that we just want to get single numbers out or 2 or 3 numbers and then increase, and as time has gone on it's gone to increasingly more complicated models. But these analytical models can only get you so far, and you end up in looking at particular situations. The reason why it's good is that it's an in situ direct measurement of permeability. So seismic is very good for determining lithology and porosity and giving you a kind of the structure of the reservoir, but it doesn't always give you the correct parameters, because lots of parameters on the permeability doesn't necessarily affect the rock properties. It isn't necessarily correlated to the rock properties, but you can have a very different permeability with exactly the same kind of rock and exactly the same kind of velocity. So I'm going to give a brief outline of what kind of data you can expect from different kinds of data sources in the oil field. So one of the key things is to actually just drill a core or take logs down a well, get information from that. That's very good quality information, and you have relatively little uncertainty. But it's really just at the log, and you've only got geology to spread that information out from the exact well site. Seismic's the exact opposite of this. It's excellent coverage of the entire reservoir, but it isn't always the same confidence, and it isn't especially for reservoir properties as opposed to the general structure. It doesn't always give it the same level of confidence. So a pressure transient test is somewhere in between these. It can give us very accurate information about reservoir properties, especially near the well, and it gets gradually less useful as you go farther out, and more parts of the reservoir get added together. And it can give us some information about the structure, about distant boundaries, but it doesn't. So it isn't just localized at the well, but it's sort of in between the two. But one of the problems with it is that it doesn't really give us directional information with a single well test, because you can always because you've only got a single measurement, you can always rotate your entire reservoir around that point and get a completely new point. So one of the key things to look at is multi-well interference pressure transient tests. So you're measuring the pressure response from several well sites, and then you start to get some directional information, but it's still going to be limited. So that's the resolution of the data, the resolution of what you can expect to invert from the data source. Another aspect is which parameters you can expect to invert, and which parameters the data is most strongly related to. So I've split those into two key categories. The lithology and porosity really fits into that as well, which is the rock properties as opposed to the permeability, which is how the fluid flows properties. And those, there's a lot of detail there, but essentially this is the summary that the pressure transient test is excellent for determining permeability because it's an exact measurement of permeability, whereas the others kind of tend to be less direct source of information about permeability. Whereas lithology, you're not actually determining anything specific about the rock. You could have the same permeability with two different rock types, so it's not determining that. So it's usually a later step in either in production or in a later step in exploration. So specific things that you'd actually want to be looking for with a pressure transient test that you wouldn't be spotting in seismic are things like fracture corridors. So you've got a region of the reservoir which has got lots of fractures that are lined up, and they're going to have a big effect on the permeability, but you may never see them in seismic because each fracture is small, it doesn't affect the porosity, and doesn't really affect the velocity. And other general small features that have big effects on the permeability and how easily fluid flows, but not on any seismic data. So as I said, there's never enough data for exact inversion with pressure transient testing because we've got a lot of symmetries in the problem. You've got this radial symmetry that you could rotate everything around. You usually have vertical symmetries that you could flip the reservoir upside down or swap layer orders around. Also, upscaling is a major issue. That small scale features we're never going to detect because you could replace lots of small scale features with a single smoothed out permeability field, and it would have the same pressure response. So it's going to be very difficult to determine those. So because we're going to have this significant uncertainty, we're forced to go down a Bayesian framework and talk about prior modelling to sort out some of these uncertainties that we know we're going to have. And so this is the standard Bayes theorem that we've seen in every other Bayes talk, that what we know after the test, the posterior, is simply the product of what we knew before the test, the prior, and how likely we were to get the measurements that we got given a particular set of parameters. There is a kind of normalization factor in all this, but that's too difficult to find in that problem, and so we're always just going to ignore that and have proportionality and not ever try and figure out that, because there's just too many parameters. So one thing to look at is the prior model, and in this problem, because we're using on quite a small scale, we don't always have a particularly good useful prior model for the scale that we're looking on the problem. Sometimes we have, and then we can use more detail. But usually we're just given something like a variogram, so just some function of how the variance changes as you have the separation distance. And there's usually quite a lot of uncertainty in exactly what this variogram is, and usually you've just got a few small number of parameters like the distances involved for correlation lengths of the different parameters. And so, as Chris already kind of suggested in his talk, one way, a particular simple one that fits in with traditional ideas of inverse problems is this prior model where you replace your kind of typical covariance matrix with a differential operator, and specifically you can use a differential operator that's kind of a biharmonic operator, and it's or biharmonic with a biharmonic operator plus Laplacian and then plus anything. And so it's actually quite easy to, so this is the 2D formula, but there's various formulas for actually relating this fairly abstract formula into things that really make physical sense in a kind of geological framework. So here, rho is just a correlation length, and I've missed off a sigma squared that should be on the bottom there, which is the variance at the point 1. And S is then a kind of shape parameter that you can play around with if you've got a smoothly varying initially. And so there's lots of different ways of thinking about this. What we're actually doing here, one, as Chris has already said, is Tikhonov regularization. It gives us a variogram approximated with few parameters. So this is kind of a simple kind of geological way of thinking about it, that we're trying to fit this variogram that's fairly uncertain. We want to approximate it with few parameters, and this allows us to do that. Another way of thinking about it is that it's a rational approximation of any variogram in Fourier space. So if you're just taking the first few terms in your Taylor expansion of this operator in Fourier space, of your variogram in Fourier space, because the variogram leads to this operator, and then this is sort of the first few terms in the Taylor expansion. And the other way of thinking about it, which is kind of the simplest, is that we don't want to deal with a particularly difficult AE with long-range correlations, and so we just replace it with a sparse approximant of it. So it's because it's a differential operator, it's clearly going to be a fairly sparse matrix. And none of this is essentially required for doing things. The only one that's ever going to be particularly useful to us is this last one. Making it sparse makes algebra easy, and if we haven't got a particularly good knowledge of the prior, we might as well make our algebra somewhat easier. So there's really two key approaches to inversion when we've set up this Bayesian framework. One is derivative-free methods that Dean pointed out, and these are certainly great for production matching. They give us, we've got the fact that it's data assimilation means that we can have more efficient simulation. The only questions are that if we're using ENKF, is the Gaussian approximation causing us to make errors? And particularly with ENKF, in geological applications, as opposed to say weather applications, you worry that the geological uncertainty isn't changing in time, and therefore is data assimilation appropriate? It's not 100% clear that it's exactly the same problem. The more traditional methods are derivative-based methods, which allow you to find locally the most likely parameters. So then there's questions about, is locally actually going to be okay, and that depends very heavily on the problem. The questions are, how do we find the derivatives? And I think we've already actually seen that in pretty much everyone's talk, which is a good thing to see, that it's adjoint's the way forward for that. But one of the key problems of this is, what about dealing with uncertainty, and can we produce samples? Because that's a more useful way of visualizing the uncertainty that we have. So I'm going to quickly show some results we had about the application of the ENKF to show what can go wrong, that it doesn't always work, but I think it could be made better in this case. This is probably not an entirely fair test. But this application we had, the truth model is, we have a producing well here, and we're trying to do this interference test, so measure the response between pressure wells. And so we have observation wells either side of a band of low permeability that we're trying to identify. So we have no prior knowledge of this band of low permeability. And so we have this period of drawdown followed by build-up. And so the initial priors don't capture the, they're a long way away from capturing the pressure response here. So this is the priors are the lighter lines as opposed to the darker lines of the responses from each of the wells. And the exact history match, when we do the assimilation of the data, we get an exact history match. So we managed to, all of these ensemble members collapse onto to the data, so it looks very promising. And we get our updates. But as soon as we start to re-simulate these data, the ensembles, we find that there's a very significant error, much greater than what we could be confident with the actual pressure transient test data. And the match is the average isn't too bad, but the variance is much bigger than what we would expect. So it's definitely improved things a lot compared to where we started, but it hasn't necessarily gone all of the way. So I'm not claiming that this can't be improved in many ways, but this was our initial results that we tried. So we went back to looking at the gradient techniques and seeing how we can improve these. So first of all, I think I don't really need to go through this, which is a good thing in this conference, because everybody has been using adjoint methods for the gradient, because using anything else is pretty much unfeasible. But one of the key things is there's two different kinds of adjoint methods. One is to determine the Jacobian, where you're determining the adjoint response for every single measurement. And here we've got so many measurements that quickly becomes impractical. So we've always been using an adjoint method for the gradient. So we're finding the gradient, in other words, of the gradient of our objective function. So we construct an objective function before we start calculating gradients, because otherwise things become far too expensive for us. And the standard approach for how you actually go about is solving a forward problem and then solving an adjoint problem, combining them. So once you've got the gradients, how do we actually use those to minimize our problem? And we're going to go back to the very simplest method of using things. And I apologize that I know there's much cleverer methods, but this is supposed to be kind of instructional about learning what things for what's going to come later. So steepest descent is the simplest scheme we've got, and it's simply saying that you follow against the direction of the gradient for some certain length that you have to determine. This alpha has to be determined by a line search to determine how far we need to go. And one of the things that we realized is that this is really an explicit Euler scheme discretization of this equation here. So this equation here, it's kind of understandable why we would want to solve this equation, because this equation has exactly as its steady state the minimizers, or the minimizers are our objective function, in other words the maximizers of the likelihood, and then these are the only stable steady states of this problem. So it's obvious why we would, in terms of finding the maximum a posteriori, want to find the steady states of this problem. But by using an explicit Euler scheme, we know we're going to have, there's the famous result, we're going to get conditional stability. So we can only take small steps in our search direction before we get an instability. And that's analogous to how we have to take small steps in our line search. And this can cause a real problem with our priors, because by having strong correlation between adjacent cells, which is usually what you require if your prior is going to actually stop the ill-poserness of the problem, you end up with a prior that's typically stiff. And that means your prior is causing you to take very small steps in this problem. So the way of correcting that is to try and use an implicit scheme. The problem is you can't entirely use an implicit scheme because this term is non-linear and non-local, and so it's not easy to split these up. So we end up using a semi-implicit scheme. So we have to keep on treating the log likelihood, the update function, based on our data in an explicit sense. But we at least try and make an implicit scheme for our prior. And so this is where a sparse representation of the prior is useful. We can solve things faster. And so when we do this, we get reasonably quick, even with just steepest descent, matches to the pressure data that's fairly accurate. I mean, there's some error here, but the prior could be shifting us away from the data there. And we get a response so we quickly get a response that fits the data, but this isn't going to be a particularly realistic response for the reservoir. We probably want a better sampling. It's the next key step. So how do we go about sampling? Well, this is really the reason why I introduced steepest descent, is that there's one of the ways of sampling is with this equation here. This is the Langevin equation, and essentially it is just steepest descent plus noise. So rather than just following the gradient, we add noise on as we're going on. And the nice property of this equation is that it satisfies the distribution of u. So if we start with a particular probability system of u and follow how it develops, then by the Fokker-Planck equation, we've got a model for how that probability distribution evolves. And we know that eventually, and that's a key point, eventually that distribution will converge to the distribution that we're seeking to simulate from. But there's some problems in using this as opposed to just using steepest descent, and that is, I said we were using a line search before. We have to use the line search because we can't make it fully implicit. But that's now tricky when you're dealing with a stochastic equation, because I can't just say, no, I'm not allowed to increase the value, because sometimes I want to randomly end up increasing my objective function, because that's what the stochastic equation should randomly lead us to do. You can't always go to the maximum a posteriori value. So the way of getting around this is to, rather than use the Langevin scheme to completely solve our problem, it's to use it instead as a proposal distribution for using MCMC chain with Metropolis Hastings. So Metropolis Hastings is then confirming that you've chosen a sensible search distance, so that you are getting stability, and that you are not getting biased results. So the Langevin gives us the sample distribution to put into this process. If you don't have a good distribution, you won't move particularly fast with it. But once again, this semi-implicit scheme of separating the prior into the parts that, not just treating the prior explicitly, now becomes even more crucial, because it turns out that for sampling, whereas when we were just doing gradient descent, we just needed to get to the final state. It didn't really matter what value of tau, so the value of tau here, that we were at when we got to the final state. But now it's absolutely crucial that we get the right value of tau, because that's affecting how much noise we've added. And so that means we need accuracy, and so that's kind of an idea of seeing why we need a kind of trapezoidal scheme that gives us higher accuracy. in fact, for simpler problems, this has been it's been proven by Andrew Stewart that that this using theta equals a half is absolutely crucial. That you won't get as you start refining your grid, you just won't end up converging if you don't have the theta equals a half case, because as your prior gets stiffer and stiffer, and so by doing this, we end up with something. We find in practice that we can take much bigger steps by taking this theta equals a half than we would be able to otherwise. So when we did this, so we run this sample, and you can see we did quite a lot of these things, quite a lot of samples through this process. So the objective function, this isn't a particularly good scale obviously, but it reasonably quickly got down to a level where we were happy with the mismatch between the data. But there still seems to be a kind of long trend through this period where it was gradually getting more towards the point where you could say that the distribution might possibly be stationary. I don't claim to have done all the statistical tests that we need to do on this yet. And so you can see here, this is the kind of convergence. It may well be sensible not to actually do longitudinal at this step and to start with a better guess, but we didn't at this point. We started with an initial guess that was completely flat, so we had no information from the wells. This is the same example that we saw in the ENKF one. So it gradually moves away, but you can see that noise is being added, and in these regions where we have no real information from the wells, the noise is just random. So that's in the early period here where we're still getting convergence to the objective function. And then in this later period, we're now in a situation where we're kind of in this period here, so we might expect these to be getting towards at least reasonable samples from the final distribution. And there's a clear reproducible element that's the low permeability band that we're trying to capture. And there's other features there that seem to be consistent, and that's a consequence of the prior with the data that the truth model doesn't fit into the prior in this case. And I actually think that's quite a good thing, because it's kind of a test of how good the prior is, that the prior isn't forcing us into the model. So we have so we're managing to reproduce the low permeability band, and we see as well that there's more changes away from that region, so that we can be fairly confident that this exists and that it isn't just a one-off kind of particular, just a feature of the most likely. And the pressure responses, when we compare matching these, we now get they're now fairly close to the pressure response. In fact, in many places the uncertainty is less than what we get in the pressure measurements, which also makes sense because we should have got extra information from the physical problem. So really we would expect the uncertainty of the final thing to be less, because we should have been able to reduce some of the uncertainty by looking at the problem. And they all seem fairly good. So the real problem with this method is the number of steps taken here. So this isn't number of steps, I should point out, but each one of these steps is fairly big. We can take possibly up to kind of 500 steps in total at each step. And it just depends, if you choose too big a step, eventually you start getting rejections in your Metropolis Hastings step. But it's still a lot of work in terms of numbers of simulations. So the key thing is to kind of start improving that. So in summary, this can be used to identify reservoir features, the pressure transient testing data, but there's always going to be significant uncertainty, so we've got to be dealing with prior models and Bayesian approach. And the ENKF, while it can be very good in lots of circumstances, and it can be improved as well, it can give a poor match to PTD data if you do it naively and don't worry about the fact that there's a lot of information in the early data. So gradient-based methods can be made certainly numerically inexpensive, although as Dean Oliver pointed out, they're not necessarily programmatically expensive. It can take a long time to program new features into the adjoint equation. And they provide the good match for the data, but there's quantifying uncertainty still a challenge. So the Launchpad method allows sampling, but the mixing rate is slow, and some ideas that we have about how you could improve that mixing rate is, at the moment we're using steepest descent, which is clearly not very good. And we'd like to be moving over to quasi-Newton methods, not in a standard quasi-Newton method, but in the sense of, again, trying to fit with our differential equation. So we try and make our problem more close to being the semi-implicit in the nonlinear term by approximating that nonlinear term by quasi-Newton methods. one thing that's crucial is optimize step length selection. So often if you can actually come up with a way of choosing the step length selection automatically, it would be a lot easier for us, because at the moment it ends up being a fairly manual procedure where I keep failing, so I'm going to reduce my step length. Parallel sampling of ensembler could be useful as well. So at the moment we've just been taking one initial sample and following that through. If we had several samples at once, we could follow those through, and those together could provide us with more information about the structure of the nonlinear log likelihood. And another one is parameter reduction, which always makes things easier, and there's a kind of question whether it's a good thing to do or not, and what the best way of doing it is. I'm sure it can help, but is it philosophically such a good thing? Thank you.
Very well timed. We've got plenty of time for questions. So,
very nice talk. The implicit scheme, the need for an implicit scheme is really very clearly illustrated in your talk. There's an entire literature of methods for stiff problems floating around out there, predictor corrector methods, deer, all that stuff. Has any of this been integrated into this subject?
I don't know. I definitely tried predictor corrector methods, and they sort of work, but I don't know whether they were really. I mean, I needed to do more work on them, but it seems like there's a lot of easy places to kind of bring things into this. So it's kind of a different way of looking at the problem.
so yep. Go ahead.
Oh, Richard, just a sort of a comment and a question. You know, early on you said that these are ways to make exact measurements of permeability. And then you do have a bunch of kind of, I mean, you almost contradict that with that. Okay.
Single measures of permeability, they could be single.
Okay, but even beyond that, we actually did a case a long time ago where we said you could take a pressure transient test and you could assume that you know the porosity, which is what you've done, and then compute permeability. Or you could do the other way around. You could say, I know the permeability, and you could actually match the pressure data equally well with a heterogeneous porosity field. So it's a kind of a funny thing to say that the permeability is being measured.
I think it's partly because porosity is usually a lot more well known from other data. So you can be relatively confident in porosity as opposed to there's much greater uncertainty in the prior. But certainly, I mean, this whole procedure is set up to run with uncertainty in the porosity as well. But then you also want to be thinking about the correlations between porosity and permeability in your prior. It just comes down, I think, and that's the main reason. It's not just that the pressure data is less sensitive, but it's that you've already done other measurements that are giving you more certainty in the porosity.
Any more questions?
Have you given any thought to whether or not a non-Gaussian prior might be worth using, and would that be a problem in this approach?
So it would certainly be. It certainly could well be worth using. It certainly would also be somewhat of a problem in that you couldn't easily. It wouldn't be so easy to do the implicit step because it's very easy in this case. But I don't think it's completely impossible because you'll hopefully have more information about that. I mean, the real difficulty of the posterior thing is that it's not just it's non-linear, it's non-local, and that it's and that you've got so much lack of knowledge, and you're only going to build up that knowledge over time. I think if you start being able to use this with a kind of quasi-Newton approach in that, then that would also follow that you'd be able to do similar things with the Gauss-Newton with a non-linear, with a non-Gaussian prior.
Can I just ask a little rider to that? So you gave a formula for a prior that had some parameters in.
Yeah.
So forgive my ignorance. Is there some geology in that?
There is a minimal amount of geology.
Right.
You've got a correlation length. You've got uncertainties in how much the parameters vary. You could, because it's a differential equation as well, it makes it quite easy to say, I've got one area of the reservoir that's completely uncorrelated from another area of the reservoir. Give one set of differential parameters in this part, another set of differential parameters in this part. Allows you to make it a lot more flexible in that sense. But you've got, in each region of the reservoir, you have very little parameters required. You've just got a uncertainty, a correlation length, and a final one that's kind of a quality shape kind of parameter of exactly how the variogram looks.
Just remark, you can make those parameters vary in space. They don't have to be constant.
Okay, well, I think speak again.